YouTube was kind enough to publish their deep learning architecture, at least as it was in 2016. Let's start at the bottom, where we have the user behavior data that is used to train the system. It's interesting that although YouTube has explicit ratings in the form of thumbs up, thumbs down ratings, they don't use them at all for generating recommendations because that data is too sparse. Not enough users rate videos explicitly for the data to be useful. Instead, they rely on implicit signals, such as which videos you actually watched and what you searched for. This implicit view and search data, however, is in itself sparse, and as we learned when covering deep learning recommenders, dealing with that sparsity is a huge issue when trying to apply deep learning to recommender systems. Their solution was to break up the sparse representation of video IDs and search tokens for each user into a variable length sequence of sparse data, mapped to a dense layer of a fixed length suitable for input to a neural network in an embedding layer. They simply average each chunk of the sparse input data. To say it another way, they split up each user's sparse behavior data into chunks of a fixed length and take the average of each chunk to reduce that data into a fixed length embedding layer that can be used as input to their neural network. They restrict this embedding to the most popular videos or search terms in order to keep it manageable for the scale they are dealing with. Any obscure video you watch ends up getting mapped to the value 0. This may seem like an arbitrary choice, but they experimented with other ways of doing it, including summing and taking the max value for each component. And the way the embeddings work is itself learned through gradient descent backpropagation, so their system is actually learning the best way to reduce the dimensionality of their sparse data. In this way, they've avoided the problem of only training the system on videos or search tokens that were actually invoked by any individual user. At the next layer, they combine together those averaged video watch vectors and search token vectors with any other training features they want to incorporate into their model, such as the user's geographic location, their age, their gender, and presumably other features not shown here. All of those concatenated features are then fed as input into a deep neural network trained with softmax. They settled on 3 layers. The first has a width of 1024 units, followed by 512, and then 256 at the top. This gave them a good balance of accuracy, while staying within their budget for computing hardware. The output of all this is fed into a database of nearest neighbors for each video to generate more recommendation candidates based on what the deep neural network found. The problem is then to optimally rank all of these candidates. Given their mandate to use deep learning for everything, YouTube also uses deep learning to rank their recommendation candidates to produce a final top-end set of recommendations. This isn't a new idea. It's called learning to rank, and there's a fair amount of research behind it as well. They throw as many features into this neural network as they can. They take the entire impression history for the user, that is, every video that was showed to them prior to viewing the video that generated this recommendation. These are embedded and averaged in a similar way to how the sparse view data was encoded to generate recommendation candidates. The language of the user and the language of the video are also embedded into another feature set. They also look at the time elapsed since the user last watched a video on this topic, and they look at the number of previous impressions this user had, which is actually used as a training feature in several different ways. They take the square root of this value, the square of it, and the value itself all as separate input features. This allows the system to discover super and sublinear functions, which is a neat trick. Everything is normalized before being fed into the neural network, of course, to make all of these features have equal initial weight. The output of all this is actually used to predict the expected watch time of each video, which is ultimately what the ranking depends on. They don't want to optimize on predicting just clicks on a video, because this tends to surface clickbait videos that people aren't actually interested in. If a user actually watches a video all the way through, however, that's a stronger indication of it satisfying that individual's interests. This is an important point. YouTube is optimizing for minutes watched, not for clicks, and this decision alone has motivated professional YouTubers to upload longer and longer videos in an effort to increase that watch time metric. They've sort of inadvertently introduced a new way to game the system. They also refine the actual objective function they use to produce those final results through continual A/B testing to try and find the function that best maximizes minutes watched. I think it's interesting that the need to combat the noisiness of video click data with minutes watched data has led to YouTube building a system that tries to drive watch time over all else. Fighting that noise has resulted in people spending more and more time on YouTube, and YouTube spending more and more resources to deliver all that video content. It's an example of a recommender system having consequences that are perhaps unintended. Here are some key takeaways from the paper as a whole. First, don't rely on just view data when training a recommender system. The folks at YouTube came up with as many signals as they could from the user's past behavior and the user's attributes, and for some features they also fed these in as squares and square roots in case there were non-linear relationships to be found. View data alone is too easily gamed and rewards clickbait videos that don't actually reflect a user's interests. They also withhold some information from their recommender system in order to prevent overfitting. For example, predicting a user will watch a Taylor Swift music video just because they searched for Taylor Swift isn't really helpful. They would have found that video anyhow from the search results, and the relationship between that search and that video is a little too direct. As a result, they discard sequence information and obscure the search data fed into their system to try and prevent this sort of overfitting. It's very common for YouTube users to watch videos that are part of a series. An episodic series of videos will generally be watched in order. So they need to try and predict specifically the next video a user will watch, and not some randomly held out future view. This means that leave one out cross-validation, as we've shown earlier in the course, doesn't meet their needs. They aren't trying to predict a randomly held out view, they must focus specifically on the next view. But the main takeaway is that they are ranking by actual consumption, minutes watched, and not just clicks on videos. Clickstream data is fraught with peril, and they've learned this the hard way. Another important thing you've learned is that you can apply machine learning not only to generating recommendation candidates, but also to how these candidates are ranked. The systems we've covered in this course produce some sort of final recommendation score for each candidate that you can sort to produce top-end recommendations. But sometimes there is additional information you can incorporate into that ranking, and how that information is applied can itself be learned.